Okay, hello everyone. So what we're going to do is in this video, we're going to basically dig deeper into the reactions of alkyl halides. And there are four reactions, kind of. They're pretty much three, but there are four overall. Two of them are very similar. So we can, and you would realize by the end that they're like three reactions pretty much that we are going to discuss here. Now, they're broadly classified as substitutions and elimination reactions. So what we're going to do here is start with the first reaction, okay? And this is a substitution reaction. So I'm just going to call it a substitution reaction for now, and I will come back and add a specific name for this reaction later once we've talked about the material, because I want you to see how do we arrive at this name. Okay, so once you identified what is the specific name for this reaction, we'll come back and add it in a bit. Okay, what is this first reaction that we're going to talk about? Okay, so this reaction is where what happens is if you have an alkyl halide, okay, and I'm just drawing it out like this, a very general alkyl halide. If you have an alkyl halide, when this reacts with a nucleophile, I'm going to use a nucleophile which has a negative charge on it, okay, to keep the charge balancing a little bit easy, okay. What happens is we get product where the nucleophile substitutes for the halogen, okay? So wherever the halogen is connected to the alpha carbon here. So this is alpha, halogen is connected to that. And what you see is the nucleophile is now connected to the alpha carbon. This is the overall reaction, okay? It's an SN2 reaction, okay? And what do we know about this reaction? Okay, that's something that we will discuss right now. And I think it will be a good idea to go ahead refresh some material from chapter 6, especially related to kinetics, and maybe some thermodynamics, transition states, things like that at this point, because we're going to use those terms here in this reaction. So what do we know about this reaction? Okay, so a few facts about this reaction. Okay, the rate of the reaction depends on the alkyl halide. And for the remainder of this chapter, we are going to call the alkyl halide as our substrate. Okay, that's the reactant, sort of the organic compound that is undergoing the reaction. Okay, we're going to call it the substrate. The alkyl halide or the substrate, and the nucleophile. Okay, the rate of the reaction depends on concentration of alkyl halide and concentration of nucleophile. Okay, that's one thing that we know about the reaction. Some additional stuff here. So basically subparts, rate doubles if concentration of substrate is doubled. Rate doubles if concentration of nucleophile is doubled. Okay, so the rate kind of doubles when both of these concentrations are doubled. So rate basically increases proportionately. Okay, it's like a very, it's a proportional increase. If you increase one of them, then the rate's going to double, or double one of them, the rate doubles. If you double the other one, the rate doubles. If you double both, then the rate's going to quadruple. Okay, so the rate depends on the rate of on the concentration of both, and then it is doubling with the increase in concentration of both. So that gives us some idea about what the rate law might be. Okay, so for this reaction, what that means is the rate is some constant, a rate constant, times concentration of the substrate times concentration of the nucleophile. Okay, and the overall order for the reaction is 2, because it is 1 here and it is 1 here. So this is 2, because this is 1 plus 1. Okay, and this would explain why when you double the concentration of the substrate, so if I make it 2x, then this rate would double. If I double the concentration of the nucleophile, keep the substrate the same, then the rate would still double. If I double both of them, the rate is going to quadruple. Okay, so that tells us that the order of the reaction with respect to the substrate is 1. The order of the reaction with respect to the nucleophile is also 1. And the overall order of the reaction is 2. And when we look at a rate law like this, the way we read this is the substrate and the nucleophile, they have to interact with each other, okay, for this reaction to happen. Okay, the substrate and the nucleophile have to interact with each other for this reaction to happen. In fact, what's important here is this applies very generally. Okay, generally what happens is the rate law tells us about the rate limiting step. Okay, it tells us about the rate limiting step. So what this rate law is telling us is that in the rate limiting step of the reaction, or the rate determining step of the reaction, both substrate, which is the alkyl halide, and the nucleophile must be present, and they are interacting with each other in that particular step. That is what the rate determining step is going to be for this reaction. Okay, so these are some facts. So based on some of the facts, we can basically come up with a rate law, and that gives us some sense for what the rate determining step of the reaction is. Okay, what else do we know? So I'm going to erase this, move on. Some other facts that we know about this reaction. Okay, we have X here. That. Some of the other facts that we know about this reaction are, so second fact is that if the substrate is chiral, okay, and in this particular case, I think I want to make it a bit more specific. We're not talking about chirality somewhere in the molecule, but if the alpha carbon is a chiral center, okay, so it's very specific. We're saying that this alpha carbon must be a chiral center. If that is the case, okay, then the reaction proceeds with an inversion of configuration. Okay, then the reaction proceeds with an inversion of configuration. So let's come up with an example for that. What is it that I'm trying to say here? Let's say we have an alkyl halide, which is like this. Okay, let's say this is our, so that's our alkyl halide. And now, as you can notice, this alpha carbon is chiral. So if there is a chiral center elsewhere in the molecule, that we are not concerned about, because this reaction happens at the chiral center. Okay, so if the alpha carbon is chiral, and let's go ahead and review some of our configuration skills, because that's still important. So stereochemistry, chapter 5, let's go ahead and assign a configuration to this molecule. So I'm going to say that bromine is carbon, is 1, highest priority group. This is 2, this is 3, that's 4. Okay, so in going from 1 to 2 to 3, we're going clockwise. So that means this chiral center is of the R configuration. And let's say bromine reacts, or this alkyl halide is reacting with, we need a nucleophile. Let's come up with a nucleophile. Let's say that our nucleophile is NaOCH3. Now, we've seen this molecule before in the acid-base chapter. We've used similar things. This is an alkoxide, like methoxide ion, okay? So again, remember that whenever we see a molecule like this, you have Na with something, then what that means is this Na is plus and this oxygen is minus. So that oxygen is the one which has electrons to it. So that's our nucleophile here. So this is our nuke, essentially. Okay, the sodium, it's just balancing the charge. So we can leave that out. Okay, so what happens in this reaction is the nucleophile should substitute for the halogen at the alpha carbon. So what this statement means is, when we do this reaction, okay, we're going to make this molecule as a product, plus we'll have Br minus, and the sodium is going to balance the charge there now. Sodium bromide would be the other product. And for this product here, the oxygen is 1, ethyl is 2, methyl carbon is 3. So in going from the highest priority group to the third highest priority group, we are moving counterclockwise. So that means this chiral center is S. Okay, so that is the product that we will get in this reaction. We will not make, okay, I have very little space here, but let me draw the other product. We will not this is 1, 2, and 3. The configuration that is R. This product is not formed. Okay, that's not formed. This is our product. This is the product that we get in this reaction. Okay, we do not get that the molecule with the R configuration. Okay, so that's another fact that we know based on experiments. Like when people were trying to develop a mechanism for this reaction, these are the sort of information that they had. So they knew that if you started with an alkyl halide in which the alpha carbon was chiral, then the reaction proceeds with an inversion of configuration. So if you started with an R chiral center, you're going to get S, sorry, in a product. Or if you started with an S configuration, you're going to get an R chiral center in your product. So the configuration would invert. It will not be retained in the reaction, okay? So that's another data point. The third piece of data is that the substitution is fastest for methyl halides, okay, and does not happen for tertiary alkyl halides. Okay, so the methyl halides, they react the fastest, and tertiary alkyl halides just do not react under this reaction. So you're basically coming up with a reactivity order. So the reactivity order for alkyl halides, okay? The reactivity order for alkyl halides is methyl halide is faster, okay? So this is the fastest actually. So that's the fastest compared to we can call a primary alkyl halide. These are faster than secondary alkyl halides, and tertiary alkyl halides, they do not react under these conditions, okay? These are the fastest, these are the slowest. Tertiary alkyl halides just do not react, okay? So this is the reactivity order for alkyl halides. So we have some evidence here, okay? So we know that the general reaction is basically an alkyl halide reacting with a nucleophile where there is a substitution going on. The nucleophile substitutes for the halogen to give us the product plus the halide. But we have these additional pieces of evidence which suggests that, you know, methyl halides are the fastest, tertiary alkyl halides do not react, and then the stereochemical evidence where if the alkyl halide has a chiral center in it, the alpha carbon is chiral, then the reaction must proceed with an inversion of configuration. So when we are trying to come up with a mechanism for the reaction, our mechanism should capture all of this data. It should be representative of all of this data, you know. It cannot fail any of these evidences. Now, this is not like the entire evidence. There are other things. Let me just get a drink quickly. there's other evidence. All we are saying is these are some of the very important points, and our mechanism should accommodate all of these observations. You know, it cannot basically flaw any of these things. Okay, so what sort of a mechanism is it then, you know, if all of this has to be applicable? So based on all of this evidence, scientists, they came up with a mechanism for this reaction. And this mechanism is a concerted process, which basically means it's a one-step process. Okay, they came up with a mechanism that has only one step in it, and that mechanism accounts for all of these observations, okay, whatever we had so far. So the mechanism is kind of very simple. In fact, the simplest of the mechanisms that we'll see throughout organic chemistry. Okay, we're going to start with one step here, and we'll go to mechanisms which are like 4, 5, 6, 7 steps, you know, depending on the reaction. So this is the simplest of the mechanisms that is possible. So the mechanism is this. What scientists suggested is you have your nucleophile. I think I should write a little bit bigger. They suggested what happens in the reaction is the nucleophile reacts with the alkyl halide. Okay, and I'm going to bring in some stereochemistry here, just draw it. Okay. And let's just say these are both hydrogens. It's a primary alkyl halide. So what they proposed is, and the same mechanism is applicable for secondary and tertiary. And in fact, we are using it for, actually, let's just start with a methyl, you know, and we'll just keep it simple. Okay, let's say this is a methyl halide. Let's go specific. So we are talking about methyl bromide here. So whatever we learn here, this is applicable to primary, secondary, and tertiary. Now, tertiaries do not react, but this mechanism would also explain why tertiaries do not react. Okay, that would also be explained by this mechanism. So what they suggested is the mechanism is the reaction between the nucleophile. I think I'm running out of space here already. Let me draw it closer. Okay, that's our methyl bromide. So what they suggested is the alkyl halide, the halogen is del negative. Okay, the key feature of the halogen, this is del negative, which makes this carbon del positive. That's why we have an electrophilic center in the molecule. So the two features basically the halogen brings in is it makes the alpha carbon electrophilic, and it's a good leaving group. Okay, so what happens is the nucleophile uses its electrons to do an attack on that alpha carbon, and this attack is yeah, I don't think we need that positive sign there. I think we can live without it. Okay, this attack is a backside attack. Okay, it's a backside attack. B-A-C-K, backside. Backside attack with respect to X. So wherever the halogen is, the nucleophile comes from the backside. Okay, Let me grab a model so that I can show you this. So essentially what we're saying is, if this is this alkyl bromide, okay, if let's say the bromine is here, the yellow, and the hydrogens are these three black groups here, then the nucleophile, okay, it comes in from the backside. So backside with respect to the bromine. So from the opposite side of the bromine group or the halogen group, it has to attack from here. So because this is an sp3 hybridized carbon, there's a lot of room here. So the bromine, the nucleophile comes and attacks from the backside here. That is how this attack happens. Okay, and as that attack happens, okay, as this is happening, at the same time, the bromine leaves with the electrons. So both of these processes are happening at the same time. There's an attack, and then we have loss of leaving group. They are both happening at the same time. So what we can imagine is a transition state, okay, a transition state for this reaction. The transition state looks something like this. So we have hydrogen, we have hydrogen. So this carbon, which was sp3 hybridized, it becomes almost flat, so goes almost like an sp2 hybridized carbon, okay? And then we have the nucleophile trying to form the bond with that carbon. This is our alpha carbon, and the alpha carbon bromine bond is trying to break at the same point. Okay, the nucleophile is bringing in a negative charge, the bromine is leaving with a negative charge. So overall we can say that there's a del negative here and there's a del negative on this at the transition state. And so this is the transition state of the molecule. And this finally leads into our product where the nucleophile, is connected to the alpha carbon, and the tetrahedral center flips over in some sense. So essentially what we're saying is, so I think I've previously used like my hand to show this. So let's say if this is the carbon, the alpha carbon, and let's say my elbow is the leaving group. Okay, this part of my hand is the leaving group. These are the three groups. This is how it's oriented. The nucleophile comes in, attacks the alpha carbon from the backside to the leaving group. Okay, attacks from the backside, and then what happens is this tetrahedron becomes something like this. It opens up, it basically flips over like an umbrella would, like in the wind actually. Okay, so now this is my nucleophile, and these are the three groups that are on the carbon. Okay, or another sense, we had a leaving group here. This is the carbon. Nucleophile comes and attacks, and when it attacks from here, the backside, this tetrahedron, where you can see these groups are all pointing in this direction towards me now. After the attack, they become like this, where this is now the nucleophile that attacked, the leaving group's gone, and the three groups that were initially like basically pointing towards me, now they're all bending in the other direction. Okay, so that is what we're trying to capture here with this picture. So we had those basically pointing like tilted a little bit to the left here, and now those are tilting a little bit to the right there, to say that that inversion sort of thing is happening. The tetrahedron is inverting. Okay, and so plus we are going to get the halogen out. So it's all happening in one step. There's no other step. We start with reactants on one hand, we have a transition state, and we end up as products on the other side. So this is a concerted process. Okay, now because everything is happening in one step, and we already talked about the rate of the reaction, okay, the rate law, the rate of this reaction. Now, since this is a one-step reaction, okay, there's only one transition state. Since it's a one-step reaction, that one step has to be the rate determining step also, okay? So the rate of the reaction, we already said, is rate is K times substrate times concentration of the nucleophile. So this nucleophilic substitution that we discussed here, this is called substitution nucleophilic. So it's a nucleophilic substitution, and it is bimolecular. It's bimolecular. That means two things have to come react with each other in the rate determining step for this reaction to happen. So substitution nucleophilic bimolecular, and we write this as S with a subscript of N and 2, SN2, where the S stands for substitution, N stands for nucleophilic, 2 is for the bimolecular reaction. So whatever we discussed here, this is the mechanism for an SN2 reaction, a substitution nucleophilic bimolecular, or bimolecular nucleophilic substitution. Now, when we talk about this, we use these terms, interchangeably. Nobody's going to say substitution nucleophilic and bimolecular. They might just say bimolecular substitution. Okay, SN2, things like that. But they all refer to the substitution nucleophilic bimolecular reaction. So that's the mechanism of the reaction. Like I said, the simplest of the mechanisms that we're going to see in this quarter, in this semester, in fact, next semester also, okay, which has only one step. The nucleophile attacks the alpha carbon from the backside relative to the halogen. Okay, wherever the halogen is pointing, the nucleophile comes from the opposite side and leads through a transition state to result in a product where this tetrahedron kind of flips over. So it's almost like you're holding an umbrella in the wind, and as the wind blows, if it's like really high, heavy wind, right, really strong winds, then the umbrella flips over. So imagine it like that. Okay, that's the kind of flip that we're talking about. This is our halogen. This is our carbon with the groups that are tetrahedral or pointing in this direction. When the nucleophile comes and attacks from this side, from the backside of the halogen, then what we get is this here. So the nucleophile is here, the groups are now pointing in the opposite direction. Okay, so substitution bimolecular nucleophilic. Now we'll see how this explains all of the other observations. So this kind of mechanism explains why it's bimolecular. The rate depends on both of them. Now let's see, does it explain the other features of the reaction? Okay. What are the other features of the reaction? So the second thing that we noticed about this reaction was the stereochemistry. So the stereochemical outcome of the reaction. So as you can imagine, since it's a backside attack, okay, and let's go back to the molecule that we had, the example that we used earlier. Since it's a backside attack, we had, I think, a bromine, methyl, and a hydrogen here. So essentially what is happening here is when we have sodium methoxide, this is plus, this is minus. It's a backside attack again. So the methoxide comes from the backside of the bromine, okay? So this is a backside attack, comes in from the backside, bromine leaves at the same time. This is our alpha carbon, and this is del positive, the bromine is del negative. All of those things are still there. And we will not draw the transition stage here, but essentially what's going to happen in the product is now the methoxide must be connected to the alpha carbon from the left side. The bromine was on the right side, the methoxide is going to get connected to the alpha carbon from the left side, okay? And I'm basically going to invert all of these groups in the opposite direction. That's why I drew the ethyl group pointing down like that. The methoxy is connected from the left side now, and then our methyl is there, and let's say the hydrogen is there. We can draw it a little better by doing this, okay? And this is R, and we saw earlier that this is S, the other one is S. So there is an inversion of configuration. So the backside attack explains why this inversion of configuration happens. So if you started with an R stereocenter, you are going to end with an S stereocenter. If you started with an S stereocenter, you're going to end up with an R stereocenter. So let's look at an example of that, and maybe in a very different system. Okay, so let's see, we have cyclohexane, okay, and we have a methyl group here, and that's a chlorine, okay? This is our cyclohexane molecule, and we can use sodium methoxide, or we can use any other nucleophile for that matter. So let's say we're using NaCN. Again, when you see something like this, the sodium is positive, this carbon here is negative. That's our nucleophile, okay? For this molecule, let's go ahead and assign configurations. This carbon is priority 1. This carbon here is priority 2. Sorry, the chlorine is priority 1, not the carbon. And this carbon at the bottom is priority 3. So this is 1, 2, 3 counterclockwise. Okay, this is counterclockwise. So that means this chiral center is of the S configuration, going from the highest priority to the third highest priority. We are, oh, sorry. Whew, looks like I forgot. No, the hydrogen is on a wedge also. This is not S, this is actually R. Okay, the hydrogen is on a wedge here, which is not shown here. So the hydrogen here is on a wedge. So this is actually R, because in going from 1 to 2 to 3, this is counterclockwise rotation, but the lowest priority group is on a wedge. So this is R. Okay, now if you look at this picture of the alkyl halide, the halogen is on a dash. It is behind the plane of this whiteboard. And our nucleophile should do a backside attack. So if the halogen is behind the plane of this whiteboard, what's backside with respect to that? This cyanide, Cn minus, should come and attack from here, okay? From the front, essentially, from the front side, okay? And what that means is, when we're done with this reaction, we're going to draw this product as Cn now on a wedge and the hydrogen on a dash. and plus you're going to have NaCl. Now, I can confirm it if this is, since we started with an R, this must be S. And I can confirm that by assigning priorities again. So when I start assigning priorities, this carbon or the cyanide group is going to be priority 1, okay? Because it's carbon, carbon, and carbon. But then this carbon is connected to 3 nitrogens because the cyanide is a carbon-nitrogen triple bond. So this is why the Lewis structures and everything from chapter 1, it's important. Okay, once we look at a structure like that, we need to know what sort of a bond is this. So this is 1, this is 2, and this is 3. And what you can notice is going from 1 to 2 to 3, this is a counterclockwise rotation, which means the stereochemistry here is S. So that means the configuration got inverted. There is an inversion of configuration. Okay, so the backside attack explains why the configuration gets inverted in SN2 reactions. The last thing here is the order of reactivity. And we already looked at this, and what we know is methyl halides, okay? These are the fastest reacting compared to primary or secondary, and then tertiaries, these do not react, okay? Tertiary do not react. This is the fastest. So let's see if this backside attack model helps us understand why this would be the case. Okay, and so what we're looking at here is methyl primary, secondary, tertiary. Okay, so we have a carbon with three hydrogens to it. That's a methyl. So this is methyl. And then we have a carbon with X. Maybe I'll try it so that it looks like a tetrahedron a little bit more. Okay, that's a primary. Then we have a carbon with two R groups to it, which is secondary. And then finally, we have a carbon with three different R groups to it, which is tertiary. And what we're comparing here is what happens when a nucleophile comes and attacks each of these carbons. Methyl, primary, secondary, and tertiary. Okay, and as that attack happens, remember the X minus is also going to leave. Okay, but we're focusing on just the attack part of it because for some reason the methyl is the fastest. So what would help us understand why methyl is the fastest? Let's think about that. Okay, what could be different when this attack is happening? So the nucleophile comes and attacks the carbon from the backside with respect to the halogen in all of these cases. So what is different in each of these cases? And let me build something as you think about it, okay? Let me try to build something here. Okay, they're not going to look the same, but I think it's fine. So let's start here. This is a methyl, okay? And let's just use one of these, something to represent a nucleophile. Let's just say that this is an oxygen, the blue, and the blue is an, sorry. Actually, when we look at models, red is usually oxygen. So let's say that red is the oxygen, okay? This is an oxygen carbon with 3 hydrogens to it. That's what we're looking at right now. Oxygen with a negative charge connected to a carbon with 3 hydrogens. So we're looking at OCH3 here, okay? And this is a methyl. And let's just say that this is a methyl halide, maybe chloride or something. So these are all hydrogens, and that's our bromine or chlorine or iodine, any of those things, okay? And so what's happening is when we have the methyl, the oxygen comes with its negative charge and attacks that carbon, the alpha carbon, and the bromine or the halogen should leave. That's one of the cases. In the other case, let's assume that this is another carbon now, okay, with some groups attached to it. So what we're looking at right now is a primary alkyl halide. We have a carbon with a halogen, but that carbon is connected to another carbon-containing group. And again, we have the methoxide coming and attacking this carbon. It has to attack that alpha carbon, and the bromine has to leave. That would be the primary. And then we can imagine a secondary alkyl halide. This is still a hydrogen, okay, but this is halogen. That is carbon is now secondary because it has 2 carbon-containing groups connected to it. And in this case, the oxygen has to come and attack. I hope you're noticing something right now, okay? And let's assume that this is our third group, okay? This is the third group, which is there. Oops, sorry. That's our third group, okay? And this is now a tertiary alkyl halide, and now the methoxy has to come and attack, okay? So what do you think changed in going from our first case, which was the methyl, to this tertiary? So notice this is always a backside attack. The nucleophile has to come and enter this cavity to do this attack and for the halogen to leave. So what's different between this, which is a tertiary alkyl halide, does not react, okay? A tertiary alkyl halide does not react. Comparing that to a primary alkyl halide, which is actually the fastest. What's different between both of them? I hope you are thinking of sterics. Okay, when we had the tertiary alkyl halide, we had a lot of groups on all of these carbon atoms, which mean that kind of blocks the path for the nucleophile to come and attack. Or in other words, when it is just hydrogens here, it is very roomy, okay? It is very roomy here, and so there's a lot of space for the nucleophile to come and attack. So that's why methyl halides react the fastest. And as you start adding groups to this carbon, when it goes from a methyl to a primary, it's fine. There's still a lot of room for the attack to happen. You know, there's nothing wrong with this because it can come and attack. There is one group over there, but that's fine. You add another carbon. Okay, the methoxide has to come and attack. Now you notice how it's kind of getting congested in this space, okay? There's groups that are going to like build up. And when you get to like a tertiary, let's see. When you get to like a tertiary system, there's a lot of steric hindrance over here. Okay, so sterics build in, and that basically prohibits attack. And So this difference in reactivity between all of this is a direct manifestation, okay? So the difference in reactivity is a direct manifestation of attack. Okay. As a direct manifestation of the backside attack, this methyl here has the least steric hindrance. In fact, it is almost like none because these are all hydrogens. Those are small atoms. So that has the least steric hindrance. And the tertiary here has the most steric hindrance. Okay, this has the most steric hindrance. And because of that, what happens is tertiary does not react. It does not even let the nucleophile come and do that attack. That does not happen in a tertiary alkyl halide. Methyl would be the best, primary would be the next, secondary, it is slowing down. Okay, so those would be the slowest for doing an SN2 type of reaction. Okay, so that way this mechanism kind of captures all the significant features about an SN2 reaction. I'm just quickly going through the textbook to make sure that I've touched upon. There's something else that's remaining, and I know that, and I will come back to that in a separate video. Okay, so that's going to be something separate. But I think over here we just discussed the mechanism of a SN2 reaction. And what you want to remember is this works best for methyl and primary alkyl halides. Secondary alkyl halides, it's already slowing down. Tertiary alkyl halides do not do this reaction. They don't do this reaction. Okay, so we'll stop right here, and then there are some other parameters that we're going to discuss in a subsequent video. Bye.